Welcome to Spring LIB.
Okay, so I originally did this, I started working on this, and then I was talking about the signs, and I think I was getting to the point where I was confusing myself and probably confusing somebody trying to listen to me. So I decided to like redo that. Hopefully, I make the video a little more clear, but I didn't want to delete this sheet because I spent so long making it. So I'm just going to go through it. So I just wrote down the givens here: 690 nanometers, 0.66 meters is the distance between the slits. D is the distance between, here's my drawing of the two slits and then the screen. And then I'll go ahead and add this. So I'm going to say that, so we know that the first wavelength's second max is going to be right here. So right here. So that's going to be the position Y1. And then Y2 we're told is closer. So there's that. And then this distance we know is delta Y. And so we know delta Y, let's say it's just Y2 minus Y1. So this is going to be a negative number. So I'll go ahead and stick a negative right here. And then so we want to know our lambda 2. So then we want to write down our condition for a second max. It's d sine theta is m lambda, but m is 2 for the second max. Solve for theta. And then we want to actually get the position. And so that from right triangle trig, here's our triangle, here's D, here's theta, because like all the thetas kind of refer to this angle. And we know that the Y for each one is D tan theta. So delta Y is going to be, just kind of plugging in this for Y, it's going to be Y2 minus Y1, and we know it's going to come out negative. So let's just drop these. Absolute value signs. I was trying to avoid the question of whether it's bigger or smaller, but it makes sense to actually figure it out. So so here's our formula, and then I just have lambda 2 and lambda 1. That's the only difference between these two. And then I went ahead and calculated lambda 1. So that's at 3.35. And then we know that delta lambda is, oh, I wrote down the wrong thing. Glad I kind of cleared that up. So delta Y is going to be negative 1.23 millimeters. So then we know that if we take this over here, then the position of Y2 is going to be 3.35 minus 1.23. So then we can just say, so what is that? That's 1.12. So 2.12. 2.12. Again, I'm just moving this to the other side. Times 10 to the minus 3 meters is d tan. Well, this whole thing. So d tan of this arc sine of 2 lambda over d. And we want to solve for this lambda. So I'm just going to kind of do out the algebra. So let's see, divide both sides by d. So 2.12 times to the minus 3 divided by 1.6. And then we want to take the arctan of that. Okay, and then I got a number in radians. And then once I've done that, then I want to take the sine of that. I'm just kind of doing out the algebra in my head. You know, you could probably have used a small angle approximation, but since they didn't say it, it would have actually really simplified this. But we can kind of go back and compare it. So then I took the sine of that, and then I need to multiply by d over 2. And then I get 437 nanometers. So 4 into 2 sig figs, that's 440. So lambda is 440. So the small angle means that tan and sine are the same thing. So then this would just become 2 lambda over d. So you can check that that gives you the right answer. But this looks right. This is the same as I think in the book. So I think I'm just going to stop here actually.